Hey guys, so in the last video we learned about ions and cations and anions and what is required for them to lose or gain electrons. I don't feel like last video was incredibly challenging. I think for the most part it was all a review. You should feel comfortable at this point. Now we are getting into new information on what happens when those anions and those cations get together, what they form, and more in particular the properties that we see. In this week, we will do a lab where we are looking at the properties of these different ionic compounds. So it's really important that we understand the background and what we should expect to see in the lab before we actually get in there. After this video, you should be able to explain how an ionic bond is formed when electrons are transferred from one atom to another in terms of resulting electrostatic attraction. That's a long way to say you should be able to do an electron dot diagram of ionic bonds. You should be able to describe the structural arrangement of ions in crystals. And then finally, you should be able to explain how various physical properties result from the ionic crystal lattice. And again, I will explain what all of this means as we go through the video. So ionic bonds. What I expect you to know now is that we have anions and we have cations. Typically, your cations are your metals. That means they lose electrons. Your anions are your nonmetals and they gain electrons, all due to the pull that they have or that electronegativity. Now, when anions and cations lose that valence electron or those valence electrons, they become what's known as neutral or grounded. They look more like a noble gas. Again, this is all just basic recall of everything we've done in the past. Now, I don't want you to think that just because we create an anion or a cation means that that electron just goes away and it just spontaneously happens. No, that these things actually have to go somewhere. So what happens is ionic compounds are formed. And an ionic compound is an electrically neutral compound consisting of positive and negative ions. So you remember your positives are your cations, your negatives are your anions. They form a beautiful relationship because opposites attract. Positive, negative, they attract one another. So and this is all based off of transferring electrons. We are not sharing electrons. Whenever we share electrons, you're going to typically see these between nonmetals and nonmetals, and that's known as a covalent bond. We are strictly talking about ionic bonding right now. So we are transferring electrons. Electrons are being given away or taken away, if you will. And how this is done is by an ionic bond. So an ionic bond is an electrostatic force that holds ions together in an ionic compound. So an ionic compound is held together by what's known as an ionic bond. And this is just an electrostatic force. It's a very, very strong force. And this allows for a lot of properties that you see in your ionic compounds. That strength from that ionic bond is directly proportional or directly dependent upon the magnitude of the charges and inversely dependent on the distance between the charged particles. So for example, a cation with a 2+ charge will make a stronger ionic bond than a cation with a 1+ charge. Also, a larger ion will form a weaker ionic bond than a smaller ion due to the larger distance between its nucleus and the electrons of the oppositely charged ion. So I just said a lot there, and I'll talk about this more in class, but you should know that the larger the charge, the stronger the bond. Kind of makes sense, right? To show a bond using an electron dot diagram, a transfer is done from the cation to the anion. And I'm going to show you an example here in a minute. I just want to get through what I'm trying to say here. And what you do need to know is that there's always going to be a formula for your bond. So you're always going to show how many of each ion you have. So a formula unit is the lowest number ratio of the ions present in an ionic compound. So that word should not be ration. It should actually be ratio of the ions present in ionic compound. So first, I'm going to show you an example, and I'm going to use the most basic compound ever because everybody knows what this is, or at least I hope you know what this is, NaCl. Hopefully you know that that is table salt. It is sodium and chlorine, and they come together and we create an ionic compound known as table salt. And so let me do the diagram, the electron dot diagram for sodium first. So it looks something like this with one dot, one valence electron, one dot. Chlorine, on the other hand, it's in group 17. It has 7 valence electrons. So 1, 2, 3, 4, 5, 6, and 7. Now, we've talked about this already in class. If I have chlorine that wants to reach a happy number of 8, and I have sodium that wants to reach a happy number of 8, what can we do to make both of them have an a noble gas electron configuration? The best answer is we can transfer electrons. And so how we do this is we transfer from the cation to the anion. So it's very conventional to show the cation without any dots around the symbol, since the energy level that originally contained the valence electron is now empty. So because there's not as much energy coming from the cation than there is from the anion, we are taking from the metal and giving to the anion. So how we demonstrate this is we just draw an arrow from the cation to the anion, and then your final product looks like this. Na with a plus, because remember, we've lost an electron. Actually, I'm going to erase this first. I apologize. So we've drawn our arrow. Oops, that's not the eraser. We've drawn our arrow from sodium to chlorine, and then the final product looks like this. Na with a plus. That indicates that we have lost that electron to chlorine. They are still really close together to indicate that this is an ionic bond, an ionic compound. So now we have NaCl. I'm going to show you another example. Or actually, I'm not going to show you this example, but I'm going to have you try this one, and you don't have to try it. We're also going to do examples in class. But I want you to do MgCl2. Couple things to remember. Cl, how many Cl's are there? What does this number tell you? How many Mg's are there? Do the dot diagrams of each first, and then determine how I got MgCl2. I'm going to let you try that. If you don't understand, we will do this in class. All right, so ionic compounds, a really important fact to know about these is that just because I put Na and Cl together does not mean that that one NaCl, that one little molecule of NaCl exists by itself in nature. So they do not exist as discrete molecules, so like one little molecule. So it takes a whole bunch of NaCl's together that make that solid, if that makes sense. And I have a picture I'm going to show you in class. I'm not the best artist, so I'm just going to show you the picture in class and explain what I mean here. But rather than taking on that discrete molecule, or rather than looking like that discrete molecule, what ionic compounds do is they take on the form of an extended 3D array of alternating cations and anions. And what I mean by here is that you are not going to see any like ions. So you're not going to see anions and anions or cations and cations close to one another or touching one another. This entire 3D structure, this entire crystalline structure is all made up of opposite charges touching one another. So what I mean, and I'm going to draw a 2D picture of this, but I'll show you the 3D picture in class. You'll have your NaCl, positive, negative, NaCl, all interacting with one another, but you'll never see Na and Na right next to each other because those are like charges. They're going to repel each other, and that's going to weaken the bond. And we know that ionic compounds are incredibly strong. Many ionic compounds are going to take on the form of a type of crystal, but they're depending on their formula unit and their coordination number, which I'm not going to go into a lot of detail. I just want you to know this for background. They'll take on a different type of crystalline shape. You don't have to know about coordination number if you look at that in your reading. I'm not going to expect that from you. In the next slide, I'm going to talk about those physical properties, though. And the physical properties are all based off of how strongly bonded together these ions are. So like I just said in the last slide, due to the attractions between opposite charges, ionic compounds are incredibly strong. This allows for them to have incredibly high melting points. And that is why it requires such a large amount of energy to break all of the ionic bonds. So that's why that melting point is so high, because you're trying to break all of those entire bonds. And remember, these are all in different types of crystal structures. And so to break every single one of those bonds requires a huge amount of energy. Table salt has a melting point of 800 degrees Celsius. So a huge number. Generally, ionic compounds are hard but brittle. So what I mean is that they require a large amount of mechanical force to break them down. So for example, if you were to grab a hammer and you were to hammer down on a certain type of crystal, that's a force. And so one layer of ions are going to be shifted around, and this may cause like charges to come into contact with one another, and this is where the crystal shatters. And when ionic crystals break, they tend to go along a smooth plane because of the irregular arrangement of the ions. So they have a really nice arrangement. So that plane is going to be broken at a nice striking area. So if you've ever hit a crystal, you'll see that it looks almost straight when you strike it. And the last characteristic I want to talk about is that they are electrically conductive, very, very electrically conductive. In the solid state, however, they're not. You will see this in lab. We will do both conductivity of a solid and of the liquid form and see what happens there. So I'm not going to explain further on the electroconductivity because I want you to try to explain it in lab. See what's going on with the ions in comparison to a solid from a liquid. And if you don't, it's okay because I will also explain it in class. If you have any questions, please ask me on Edpuzzle. This video is a lot shorter than the first one, so hopefully I didn't go too fast.